In this lesson, we are going to take a look at the definition of a sequence and examples of sequences. We are not going to discuss whether or not a sequence converges or diverges or the limit of a sequence, so that's for another video. So what is a sequence in mathematics? There are a couple different ways to define it, but I think a good working definition to start with is it's an infinite ordered list of numbers. Every adjective there is important. So a sequence should be an infinite list. Your sequence could be 1, 2, 3, 4, 5, dot, dot, dot to indicate that it goes on. It shouldn't be the sequence 1, 2, 3, 4, 5, stop. So it's got to be an infinite list. The order matters. So the sequence that starts 1, 2, 3, 4, 5, et cetera, is different than this from the sequence that starts 2, 1, 3, 4, 5. Even if all the numbers are the same, the order is different. So it's a different sequence. I typically write sequences this way. I like to use the curly bracket symbol. Sometimes, if you're looking at a different text or source, instead of a curly bracket, you might see parentheses or even nothing at all. That's okay too. It should be clear from context that this is a sequence. Each of these items is called a term. So the A sub n are the terms in the sequence. We index them with the subscripts. So they are indexed by subscripts. In most cases, sequences start with a first term. So A sub 1 is the first term, this is the second term, third term, fourth term. Then we can't say every single term in a sequence because it's infinite, but we often like to talk in a sort of general sense about the nth term in the sequence. So here, n is a number that's unspecified. It represents a general sense of behavior. If you write out the terms in your sequence like this, it should be clear if there's a pattern. So you want to write enough terms in the sequence to notice a pattern if there is one. What we can do is write the sequence in a condensed form where we have something like A sub n, where we might indicate that we're starting at 1 and we're going off to infinity. So this would represent the sequence whose terms are A1, A2, A3, A4. If it's starting with n equals 1, you might just write your sequence like this. So this object for us will represent a sequence whose terms look like A1, A2, A3, etc. Sometimes, and it's usually a question of notational convenience, you might see a sequence start with a different index, meaning A sub n starting with n equals 0 to infinity. And that can happen. I'll try to specify if a sequence is ever starting at a different index other than 1, but by default, we'll imagine that our sequences are starting with the n equals 1 term. Okay, so let's take a look now at the types of sequences which we might have. If we're studying a sequence, usually it's understood that there's some kind of pattern here, but there doesn't have to be. The sequence 3, -1, 7, 0, 0, 2, 5, pi, e, I'm just trying to make things up like a random number generator, is a sequence even if there is no pattern to it. But for the rest of today's lessons, we're going to be looking at sequences where we can give a descriptive form to this generic term A sub n. In these two examples, we would like to take these sequences, which are given with a descriptive form, and list out the first few members of the sequence or the first few terms in the sequence. So our first sequence is the sequence that looks like 3 to the n divided by 1 plus 2 to the n. So here is like a recipe for every term in the sequence in terms of the index. So what this tells us is our first term, A sub 1, must have the form 3 to the 1 divided by 1 plus 2 to the 1. So that's 3 divided by 3, it's 1. The second term in the sequence, A sub 2, is 3 to the second power, so 3 raised to the index 2, divided by 1 plus 2 squared, so that's going to be 9 over 5. The third term is 3 cubed divided by 1 plus 2 cubed. So that's 27 divided by 9, which is 3. And then we get the fourth term, which is 3 to the fourth power over 1 plus 2 to the fourth power. So that's 81 divided by 17. See if you can write down the fifth term. Okay, the fifth term, a sub 5, is 243, that's 3 to the fifth power, divided by 1 plus 32, which is 33, and that simplifies to 81 over 11. Then we know the nth term is given to us by this expression. So it's 3 to the n divided by 1 plus 2 to the n. If I wanted to start writing out this sequence, I would write 1, 9 over 5, 3, 81 over 17, 81 over 11. Okay, so that was our first sequence. For the second sequence, we'd like to list out the first 8 terms of sine of n pi divided by 2. Okay, see what you get when you do this. So n here represents indices. So first n will be 1, then 2, 3, 4, 5, 6, 7, 8. So write out the first 8 terms of this sequence where every single term is given by this formula in terms of the index. All right, so sine of 1 pi over 2 is sine of pi over 2, which is 1. Then sine of 2 pi over 2 is sine of pi, which is 0. And then the next one would be sine of 3 pi over 2, which is negative 1. And then sine of 2 pi, which is 0. And then we're back around to sine of 5 pi over 2, which is positive 1. And then 0, negative 1, 0, positive 1, 0. I'm writing more than I asked you to, but that is our sequence. So we get this repetitive sequence where we have 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, et cetera, et cetera. So if you need to write a sequence that kind of jumps around in this way, you can use trigonometry to get that. Now let's go the other way. In these examples, given the first few terms in a sequence, let's see if we can write down a generic expression representing the nth term in the sequence. So our first example is the classic 1, 2, 3, 4, 5, 6, 7. So the first term is 1, the second term is 2, the third term is 3. That means the nth term is just n. So we'll say that this sequence can be written more concisely as n. Okay. The next term we have alternating negative 1, 1, negative 1, 1, negative 1, 1. Here's what we want to think about for that. Negative 1 to even powers is 1. Negative 1 to odd powers is negative 1. So then you just say, well, are the indices even or odd when we have a negative or positive version of this number? I think I'm overcomplicating it. Let me just write it down. This is the sequence negative 1 to the n. So negative 1 to the 1 gives us our first term. That's the negative 1. Negative 1 squared is positive 1. That's our second term. The negative 1 cubed is negative 1 again, then positive 1, negative 1, positive 1. So you can see that gives us the sequence that we started with. For the third example, however, we have a difference in the signs. So this time we're starting with positive 1, then negative 1, then positive 1. So we need to take this in and adjust it. This would be negative 1 to the n plus 1. That's one way to do this. Or you might see negative 1 to the n minus 1. Either one has the same effect. When n is even, this will be negative. When n is odd, this will be positive. Okay, for the next sequence, we're looking at 1 over 2, 2 over 3, 3 over 4, 4 over 5. What do you think that's going to be? Well, the numerators match the index. So 1, 2, 3, 4, 5. The denominators are 1 higher. So this is the sequence n over n plus 1. For the final example, take a moment. The numerators are always 1. See if you can come up with a pattern and write it in terms of the index n for the denominators. All right, for this fifth example, numerator is always 1. Maybe skip the first denominator. The second denominator looks like 2 squared, then 3 squared, 4 squared. So we see these perfect squares in the denominator. Each one is actually the index squared, and that does match what's happening in the first term as well. It's just that 1 divided by 1 squared is more concisely written as 1. Okay, so this is an example of kind of spotting the pattern and to get a general expression for the sequence given the first few terms. These were not too complicated, so let's look at a harder example. Now let's find a formula for the nth term of this sequence, which starts with 4 over 5, negative 16 over 7, 64 over 9, negative 256 over 11, et cetera, et cetera. So there's a lot more going on with this sequence than in the previous examples. What I'd like to do here is just kind of break it down piece by piece. We have different characteristics in the terms in the sequence. The first one that jumps out at me is the fact that they all have alternating signs. So we have positive, negative, positive, negative. Let's come up with a component that reflects that switching behavior. So it's either going to be negative 1 to the n or negative 1 to the n plus 1. Since the first term is positive, that means that my first term needs to be raising negative 1 to an even power. That indicates that somewhere in my sequence description, I should have a negative 1 to the n plus 1. So that when n equals 1, we're squaring. When n equals 2, we're cubing. That's going to get us back this negative sign. All right, that takes care of the plus minus aspect of the sequence. Let's look at the numerator. Here, given that I've already done the signs of the terms, let me just focus on the number that appears in the numerator. We have 4, then we have 16, then we have 64, then we have 256, et cetera, et cetera. Then you just think, do these numbers have anything in common? And looking at it, it's like, they could be perfect squares, they could be multiples of 5. Here, what I see is powers of 4. So this is 4 to the 1, 4 squared, 4 cubed, 4 to the 4th power. Might need to check the others are 4 to the 5th and 4 to the 6th power. So this is going to be 4 to the nth power. Had the first term started with 16 and then 64, I might have done something like 4 to the n plus 1. So you can make a little adjustment like this. But here we really do have 4 to the 1, 4 squared, 4 cubed, 4 to the 4th. Then for the denominator, we have 5 to 7 to 9 to 11, etc. This is going up by 2. That's not hard to recognize, but then you have to write down an expression in terms of the index n. We want to start at 5 and then go up by 2. So if you're stuck, some people are good at kind of writing this down right away. If you're stuck, here's one tip. That is, if your sequence is increasing by the same amount, so it's up by 2, up by 2, up by 2, that's like traveling along a line of slope 2. So start to write down a line with slope 2. How about I write 2n plus b? So instead of x, I'm writing n for the index. And now let's just plug in that when n equals 1, y is 5. That will give me the missing b. So 5 is 2 times 1 plus b. So this tells me that b is 3. So my formula here should be 2n plus 3. So if you check that, 2 times 1 plus 3 is 5. 2 times 2 plus 3 is 7. 2 times 3 plus 3 is 9. So that does take you through this progression 5 to 7 to 9 to 11 to 13, et cetera, et cetera. Now we just put it all together to get that this sequence is going to be this times this divided by that. So negative 1 to the n plus 1, 4 to the n, divided by 2n plus 3. Okay, so that is this sequence. The examples we've looked at so far, we had explicit formulas for the terms in our sequence. So if I gave you a formula for a sub n, you could immediately tell me what a50 is by plugging 50 in for n. Sometimes sequences are defined recursively, which means that you start at the beginning and you build up later terms based on what you already know. So let's look at these two examples. For this first one, we are being given what's called a seed. It's like you plant it, and from that, your sequence grows. We know that the first term in the sequence is a sub 1. Sorry, the first term in the sequence, a sub 1, is 3. I was about to write down 1, but our first sequence term is 3. Now, this expression tells us that a sub 2 would be twice a sub 1 plus 1. So it's like to get to the next term, you're going to use this formula based on what you just wrote down. So 2 times 3 plus 1 is 2 times 3 is 6 plus 1 is 7. Now, the third term in our sequence is 2 times the second term in the sequence plus 1. I'm getting all turned around with these numbers. Okay. So we're going to use this formula in terms of the previous term to get the next term. So 2 times 7 plus 1 is 15. And then 2 times 15 plus 1 is 31. Then 2 times 31 plus 1 is 62 plus 1 is 63. So this is this sequence which has been recursively defined where we were given the seed and then we have to work out the future terms in the sequence based on the previous term. This sequence actually can be put in an explicit form. So you can come up with a recipe for the terms in the sequence, a formula for the nth term, if you will. Take a moment and see if you can work out what that is. Here's what you might have noticed. Each term in the sequence looks like 1 less than a power of 2. So 3 is 1 less than 4, 7 is 1 less than 8, then 15 is 1 less than 16, and we have 32 and 64. So if I can figure out how to write down these terms, I just have to subtract 1 to get back the sequence. So this is 2 squared, 2 cubed, 2 to the 4th. That's 2 raised to 1 higher than the index. So 2 to the 1 plus 1, 2 to the 2 plus 1, et cetera, et cetera. So 2 to the n plus 1 gives me the 2 power, and then subtract off 1 to get back the actual sequence itself. Let's look at this other example. This is a famous example. So here we want to write down the first 10 terms of this sequence. Here we have 2 seeds. We're being told that the first 2 terms in this sequence are 1. And we must know 2 terms in order to get the next term, because what we're being told is that a sub 3 must be a sub 2 plus a sub 1. So a sub 3 is this plus this, that's 2. Okay. Then a sub 4 is a sub 3 plus a sub 2. So a sub 4 is 2 plus 1, which is 3. And then a sub 5 is a sub 4 plus a sub 3. So 3 plus 2 is 5. Then 5 plus 3 is 8. 8 plus 5 is 13. So 13 plus 8 is 21. 21 plus 13 is 34. Then we would get 55. And I'm going to write dot, dot, dot. I don't know how many I wrote down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, perfect. Okay, these are the first 10 terms in a sequence you might recognize. This is the Fibonacci sequence. This is a famous sequence that goes back to the Middle Ages with Fibonacci. Did I spell that right? Yes, I think so. Fibonacci. Okay. If you're wondering if there's an explicit form like this for the Fibonacci sequence, there is, but it's a lot more complicated than this expression. If you're interested, you might want to look at Binet's formula. This gives you a specific way to calculate the nth term of the Fibonacci sequence without needing the preceding terms. Because right now, if I said, what's the 11th term in the sequence, I don't have a formula that you could plug into to get a sub 11. You would have to say 34 plus 55 is 89. So these are recursive sequences because they're being recursively defined, where the next term in the sequence depends on previous information. Let's go through the definitions of some adjectives that we might want to apply to sequences when we start observing the same kind of behavior over and over. So, an increasing sequence is one where the terms seem to go up. In particular, we'll say a n plus 1 is greater than or equal to a sub n for all n. I'm going to write for all with this upside down a symbol. So in math, whenever you see upside down a, it means for all. So terms in the sequence are at least as big as the previous term. On the other hand, sequences are decreasing if a sub n plus 1 is less than or equal to a sub n for all indices n. Let me give you a minute to assess whether or not a constant sequence, like the sequence 1, 1, 1, 1, 1, is increasing or decreasing. The answer is that a constant sequence is both increasing and decreasing because the inequalities here are not strict. So in other words, adjacent terms can be equal, and in fact, even if every single term is equal, the constant sequence matches the definitions of both increasing and decreasing. If you wanted to, you could say a sequence is strictly increasing to mean that this inequality here is strict. That means the sequence only gets larger as you go through the terms. Sometimes we don't care if the sequence is going up or going down, but what we care about is it does trend in one direction. So we have this general word monotone. We say a sequence is monotone if it's increasing or decreasing. So a monotone sequence is one that is either an increasing sequence or it's a decreasing sequence. Sometimes you might say monotone increasing, kind of putting both those words together, or monotone decreasing. I say that a lot as well. Lastly, we say that a sequence is bounded if there exists, so that's what this backwards E means, there exists a number m greater than 0, so that if you take the absolute value of every term in the sequence, so I'll write absolute value of a sub n to mean every term, this size, the absolute value of a sub n, is less than or equal to this number m. So this inequality is true for all indices. Just a little note here, brought in another kind of funny letter. Backwards E in mathematics means there exist. So we use these phrases for all and there exist so often that we have this universal shorthand for how to write those. This number m is called a bound. And there's no unique choice for m. So if m works, so does m plus 1. It would also satisfy this inequality by default. So to say that a sequence is bounded, you just need to find one good bound, which is greater than or equal to the size of every term in the sequence. Let's test our understanding of those definitions on these four examples. So for each of these sequences, is the sequence monotone? So is it increasing or decreasing? And also, is it bounded? This first sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, et cetera, it is monotone because it's increasing. So you could just say monotone. Here I'm going to say monotone increasing. However, it is not bounded. These terms are going to grow without bound. On the other hand, for the second example, we have this alternating sequence, negative 1, 1, negative 1, 1. This sequence is not increasing or decreasing because it's jumping back and forth. However, it is bounded. Started to write the word by before I finished the word bounded. This is bounded by m equals 1. So every term in the sequence satisfies that its absolute value is less than or equal to 1. For this third example, we have a half, 2/3, 3/4, 4/5, then 5/6, et cetera, et cetera. This sequence is increasing. So this is a monotone increasing sequence. And it is also bounded by 1. For both of these examples, 1 is the smallest bound that you could give, but it's not the only correct bound. You could say it's bounded by 2 or it's bounded by 10. Those numbers would also work as bounds. Often we do like to give kind of the best bound, if you will, but it's not a requirement to meet the definition of bounded. Okay, for this final example, we're looking at 1 over n squared. So we have 1, a fourth, a ninth, a 16th, et cetera, et cetera. This is decreasing. So this is monotone decreasing. All of the terms are between 0 and 1, so this one is also bounded by 1. Okay, so I hope these 4 examples illustrated those definitions. This wraps up this video where we looked at the definition of a sequence, several examples of sequences, and here are some characteristics of sequences. In the sequel to this video, we are going to look at the notion of the limit of a sequence. So sometimes you might be able to look at a sequence and say, hey, this is trending somewhere. So we will define what it means to say that a sequence converges or doesn't converge, as well as look at some results about the limits of sequences.